Hi, everyone, and welcome to the first lecture in Finite Mathematics, Math 1110. I am going to be making videos like this and sending them out at regular intervals. I will always announce a new video by email, and I will try to do the same by Canvas. Please keep an eye on your email and also on Canvas. This is going to be our first lecture. And during this lecture, I will do some examples, I will define some things, and I will give a homework assignment at the end. In order to increase our chances for success in this course, please stay up with the videos and do the homework from the text in timely fashion. And if you have questions about some exercises, please feel free to email me at my Troy address, and we'll work them out. You know, when I was a student, I went to school in the summer quite often, and without a doubt, I got my best work done in the summer. It's a good time to be in school. The weather's usually very nice, but things are still kind of laid back and comfortable, and yet we can still get a lot done. I know when I was a student, I always did. My best courses were always in the summer, and I think maybe that experience can be true for you too. So let's get on with our first lecture in finite math. Our first order of business in this class is to do a study of sets. Don't think that this is trivial. Our second topic in this course is probability, and in order to do well in probability, we have to have a very good understanding of sets. So this may seem trivial at times, but it's not going to stay trivial forever. We're going to get into sets. We're going to do set operations. And these set operations are going to be invaluable to us when we do probability. So don't look at this and go, oh, no, not this stuff. A good understanding of sets and set operations is important in our next topic, which is probability. So let's get on with sets. And we define a set to be a collection of objects. And that's the best we can do. That should be good enough. The objects, another definition, the objects that are contained in a set are called members or elements. So any object that's contained in a set is called a member or an element of the set. And more often than not, we use the expression element to describe an object that's contained in a set. Now, let's look at an example. Let capital S be the set days of the week. The members or the elements of the set S are Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. These are the elements or the members in the set S, days of the week. Having given this example, we need to say something else about a set. A set should be well defined. And a set is well defined if its elements can be determined with absolute certainty. Well, what am I talking about here? Let's illustrate this with another example. Let's stick with the set S being the days of the week. Now, I claim that S, the set of the days of the week, is well defined. Now, why do I say that? With absolute certainty, that we can determine what the elements of the set are. These are the days of the week. With absolute certainty, these 7 days are in the set S. And it's also possible to determine what elements are not in the set. This element here, this object, refrigerator, is it an element of the set S, the days of the week? Nobody who has any measure of sanity is going to say, well, refrigerator, it might be a day of the week. Nobody's going to say that. With absolute certainty, we look at this thing and say, nope, this is not an element of set S, the days of the week. And the same thing with bullfrog. Nobody with a measure of sanity is going to say, well, maybe it is one of the days of the week. Nobody says that. With absolute certainty, we can say this is not an element of set S, the days of the week. So the set S, days of the week, is a set that's well defined. Having looked at this example, let's look at another example. let S be the elements, let S be the set whose elements are great singers. What do you think? Is this set well defined, or is this set not well defined? If we think about it for a minute, we're probably going to come to the conclusion that S is not well defined. And why do we say that? Well, membership in this set is a matter of opinion and not something that can be decided with absolute certainty. And I'll give you some examples. Now, my father would look at this object and say, oh, definitely this is in the set. This is first on the list in the set of great singers. Now, I might look at this name and say, maybe. I'm not going to argue the point, but he doesn't do much for me. Now, my older brother would say, this element's definitely in the list. And you know what? Our father would say, this guy, he's a bum. He can't carry a tune in a bucket. And my older brother would say, you don't know anything. You're so old, you don't. This is the greatest singer who ever lived. They don't call him the king for nothing, you know. And now my grandkids, hey, she's it. She definitely belongs in this set. She is a great singer. And I think anybody my grandkids' age are going to say, yeah, I have no problem with that. Now, my father would listen to something she sang and say, oh, how can you kids listen to that stuff? No, oh, she's terrible. Well, the fact of the matter is that the elements of this set, the set of great singers, cannot be determined with absolute certainty. Membership in this set is more a matter of opinion and a matter of personal taste rather than absolute certainty. So this is a set that is not well defined. And essentially for the remainder of our discussion of sets, this lecture and beyond, we're going to be concerned with sets that are well defined. Sets whose elements or members can be determined with absolute certainty. Okay, everybody. 3 ways of defining a set. Some sets are not easily defined just by saying their elements are the greatest singers who ever lived, and so forth. So we have 3 generally accepted methods of defining a set. In other words, defining with absolute certainty the criterion for membership in a set. And the first way that we can define a set is by description. When we define a set by description, the conditions for membership in a set are described in a well-defined manner. By description, we determine with absolute certainty what objects are elements of this set and what objects are not elements of this set. And here's an example. Let S be the set of elements, or rather, let S be the set whose elements are the days of the week. Well, we already know that this is a well-defined set. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, they are elements of this set. They're the only elements of this set. Refrigerator, bullfrog, they're not elements of this set. So here we have defined the set S by description. We have literally described what the conditions for membership in the set S are. Let's look at another example. Let S be the set whose elements are those students who are currently enrolled in Dr. Rossi's finite math class. Again, S is described, or S is defined by description. And in my description, have I defined membership in set S by a well-defined way? Yes. Those students who are currently enrolled in my finite math class, the membership in this set can be determined with absolute certainty. At this very moment in time, either a person is enrolled in my finite math class or they're not. There's no gray area there. Now, sometimes description is the best way to define a set. Sometimes it's not, which is why we have two other methods. Let's look at the second method, the roster method. As I mentioned before, there are two other methods of defining membership in a set. The second method is the roster method, and the method is exactly what the name implies. The elements of a set are stated in a list or a roster, and we do it in the following manner. We have the name of the set and then an equal sign, an opening set of brackets, a closing set of brackets, and in between we have the members or elements of the set written down explicitly. So we would read this the following way. S is the set whose elements are first element, second element, third element, ... last element. Here are some examples. S is the set whose elements are Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So the set that we defined earlier using description, we can also define using the roster method. Let's look at another example. S equals the set whose elements are Raiders of the Lost Ark, Temple of Doom, The Last Crusade, Kingdom of the Crystal Skull. Now, if I were to define this set by description, or if you were to define this set by description, how would you do it? You'd probably say S is the set whose elements are Indiana Jones movies. Well, we've defined the set using the roster method instead. We've listed explicitly all of the elements of a set. These are the 4 Indiana Jones movies. We listed them explicitly. Now let me ask something. Suppose that we want to use the roster method, but there are so many elements in the set that it would be impractical to write down all of the elements. There are too many elements in the set in order for it to be practical for us to define the set using the roster method the way we've done so far. And yet maybe it would be even more difficult to define the set using description. Well, it turns out we can still use the roster method in some cases. And I'll show you how in just a minute. Back to our topic at hand. Suppose that our set is so large that it's impractical to list all of the elements, and yet we still want to use the roster method. Can we do it? And the answer is yes. We can still use the roster method, and we'll have to use a literary device called an ellipsis. Dot, dot, dot. This is what we call an ellipsis. Dot, dot, dot. And the meaning of this, dot, 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 it means and so on, or it means continuing in the same manner. So here we have a set with finitely many elements, but it's a large set. It has 100 elements. And we look at this thing and its elements are 1, 2, 3, dot, 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 99, 100. Well, this dot, dot, dot tells us the listing of the elements continues in the same fashion. 1, 2, 3, okay, 4, 5, 6, 7, 8, 9, all the way to 99, 100. So this set S is the set of all whole numbers between 1 and 100 inclusive. Now we can do this also with sets whose elements are not numerical. Look at this example. S equals January, February, March, dot, 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 November, December. This dot, dot, dot means and so on, or in like manner. January, February, March, and so on, November, December. We look at this and clearly we know how to interpret it. We've listed the first 3 months of the year in order. So following in this order, we have April, May, June, July, August, September, October, November, December. So it is possible to use an ellipsis on a set whose elements are not numbers. Let me ask another question. Do you think that we can define the elements of a set if the set contains infinitely many elements? Suppose that we have a set whose elements are infinite in number, and we still want to use the roster method. Can we do it? Think about it for a second. How do you think we might use the roster method to define a set that has infinitely many elements? You may have an idea, so let's give an example. We can define a set using the roster method, even if the set has infinitely many elements, and we just use the ellipsis again. Here's an example. Two, 4, 6, 8, and so on. Well, if most people look at this, they're immediately going to say the elements are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, etc. This is the set of all positive even numbers. And what about this? Okay, 3, 6, 9, 12. What would the next number in the set be? Let's see. Each number after the first is 3 larger than the one it follows. So 6 is 3 larger than 3, 9 is 3 larger than 6, 12 is 3 larger than 9. So I'm guessing the elements are 3, 6, 9, 12, 15, 18, 21, 24. Now another way of looking at this is to notice that all of these numbers are divisible by 3. So this must be the set of all positive numbers that are divisible by 3. 3, 6, 9, 12, 15, 18, 21, etc. Now we can do even better than that in some cases. Look at this example. In this example, the ellipsis here indicates that the elements of the set, infinitely many of them, that precede -6 are elements that continue in the same order. So if we were to go backwards, we'd have 0, -2, -4, -6, then what? -8, -10, -12, and so on. And continuing in the forward direction, 0, 2, 4, 6, 8, 10, 12, 14. So this would be the set of all even numbers positive, negative, and 0. So the set of all even numbers, not just the positive even numbers, but the positive even numbers, the negative even numbers, and 0. And we can define this set using the roster method and the ellipsis. Now, what happens if we have to define a set and description doesn't work very well, and the roster method doesn't work very well either? Well, it turns out that there is a third method, and that third method is called the set builder method. We'll look at that next. Okay, another example. The third way to define a set using what we call set builder notation. And when we do this, we write a statement that has this appearance. So let's go over carefully what this set of symbols actually means. This is the name of the set, and this can be translated equals or is. This opening bracket is translated the set of. So these three symbols would read S is the set of, or S equals the set of, all elements X, and this vertical bar we translate as such that. And what follows the vertical bar is a criteria for membership in the set S. Now, you know what? That's a lot to take in all at once. So let's do a couple of examples where we use this notation. And then under the notation, we'll write out in English what that statement in mathematics actually means. Let's do a couple of examples using set builder notation. Let's diagram this now. The set S equals or is. This is translated, let's see, how do we translate this? Do we remember? If you said the set of, then you're right. This is translated all elements X. And what about this? Do you remember how that vertical bar is translated? This means such that and then the condition for membership. X is a real number and x is less than or equal to 10. Ooh, I left something out here, didn't I? All elements x, yes, all elements x. S is the set of all elements x such that x is a real number and x is less than or equal to 10. Let's try another one. And let's call this one G. Okay. The name of the set, G, and we can translate this as is or equals, either one, and how is this translated? How do we translate this? This is the set of and I'm going to get this right this time. I'm not going to leave off a word. This is all elements x. There we go. Now what about this vertical bar? How did we say that we translate that? Such that. That's right. Such that. Okay. So here's what we have. G is the set of all elements x such that x is a real number and x squared equals 2. Now, maybe there's an improvement that I can make here. This is kind of wordy. X is a real number. So I'm going to introduce some symbols, and then we'll revisit the set builder notation. This capital N has two vertical bars coming down on the left. In your text, this is just going to appear to be a bold-face capital N. This capital bold-faced N represents the set of all natural numbers. That is, the set of all positive whole numbers. So if we write this in roster notation, this is what the set of natural numbers is going to look like. 1, 2, 3, 4, 5, 6, 7. So capital bold-faced N is the set of natural numbers. This is a capital bold-faced Z. This is the set of integers. And the set of integers is the set of all whole numbers. That's positive, negative, and 0. So if we use roster notation for the set of integers, we denote the set of integers this way. The set of all positive whole numbers. The set of all whole numbers. Negative, positive, and 0. That's what we call the integers. And we denote that with a capital Z. Now, I guess there's one more set of numbers that I should introduce. I may introduce others later on. This capital bold-faced R represents the set of all real numbers, R for real. Now, I don't think I can represent that with roster notation, but I will explain it a different way, descriptively. The set of real numbers is also the set of all points on the number line. And this would include whole numbers, fractions, decimals, even decimals that don't terminate. Decimals that just go on and on and on forever, they're real numbers. A real number is any number that can be represented as a decimal, whether it's terminating or non-terminating. So we can look at the set of real numbers as all points on the number line. The whole numbers, the fractions, the decimals, all of those are real numbers. Now there's one more symbol that I should throw at you. This symbol denotes membership in a set. So maybe I should write that down. So it denotes membership in a set. Exactly how might we use this symbol? This statement says 2 is an element of this set. Okay, what about that? Three is an element of, and then this thing, the set of natural numbers. Let's do one more. We'll let capital S be the set of all states in the US. And we could write this statement. Alabama is an element or a member of the set of states in the US. There, put the finishing touches on it. Now, what happens if we have something like this? Well, let's see. Ontario is an element or a member of the set of states in the US. That's not true, is it? Ontario is not a member of the set of states of the US, is it? So here's what we do. We draw a line through this symbol, and that changes the meaning of the symbol. Ontario is not an element of the set of states of the US. but it is an element of the states of, or the provinces of Canada. So the membership sign with a line drawn through it is translated is not an element of, or is not a member of. Now this capital bold-faced N, do you remember what that was? See, this is the set of natural numbers, or counting numbers, 1, 2, 3, 4, 5. So natural numbers, that's the set of all positive whole numbers. 1.5 is not an element of the set of natural numbers. And maybe we could say that a little bit more concisely. 1.5 is not a natural number. So let's revisit this statement. 2 is an element or a member of the natural numbers. So 2 is an element of, or 2 is a member of, the set of natural numbers. Now, we can make this a little bit more conversational. But we might say it like this. 2 is a natural number. We could render the expression that way. Okay, I guess the reason that we took this little detour is because we wanted to make our set builder notation a little bit less wordy, a little bit more conversational. So let's try the set builder notation again, okay? Here's our set S, and this can be rendered equals or is. What about that opening brace there? How do we translate that? You remember? S is the set of and this guy, all elements X. Okay, vertical bar. How do we translate the vertical bar? S is the set of all elements X such that what about that? X is a real number and X is less than or equal to 10. That's how we translate it. And from here, we can probably make it a little less wordy than it already is. Let's see, what would be a more natural way of saying this? See, S is the set of all X such that X is a real number. Maybe we'd say S is the set of all real numbers X such that X is less than or equal to 10. A little bit more natural. Okay, let's look at a new concept. Equal sets. The definition says sets A and B are equal if they have exactly the same elements. Notice what it says, if they have exactly the same elements. Now let's notice what it doesn't say. It doesn't say sets A and B are equal if they have exactly the same number of elements. Doesn't say that. It says they're equal if they have exactly the same elements. So, in this example, what sets are equal? Let's see, is A equal to B? No, because A has a 1, but B doesn't. Is A equal to C? Ooh. Well, let's see. A has a 4, but C doesn't have a 4. So A and C aren't equal. Is A equal to D? Let's see. A has elements 1, 2, 3, 4. And D has elements 1, 2, 3, 4. So A is equal to D. They have exactly the same elements. And we write it this way. This means they're exactly the same set, they just have different names. Now, are any other sets equal? Is B equal to C? Well, let's see. B has a 4, but C doesn't. So B and C are not equal. Is B equal to D? Well, D has a 1, but B doesn't. So B is not equal to D. So it looks like B is not equal to any of the sets other than itself. Is C equal to D? Well, D has a 4, but C doesn't. So the only two sets here that are equal are A and D. They have exactly the same elements, and so we write A equals D. Now, let's look at a related concept. Let's see. A definition. A cardinal number. This is how we denote the cardinal number of a set A. And it's the number of elements a cardinal number is the number of elements in the set A. Now let's look at this same example. The cardinal number of A, which I write this way, and I like to think this N stands for number of elements. So the cardinal number of A, or the number of elements in A, 1, 2, 3, 4. Okay. Move on. Set B. The cardinal number of B, little n of B, the number of elements, 1, 2, 3. And cardinal number of C, there are 3 elements, 1, 2, 3. So cardinal number of C is 3. And then last but certainly not least, D. There are 1, 2, 3, 4 elements in D. So the cardinal number of D is 4. Two sets A and B are equivalent, not equal, but equivalent exactly when they have the same cardinal number. Or to put it another way, exactly when A and B have the same number of elements. Well, let's go back to this example. It's an easy one to work with. Okay, I guess we're going to consider this example again. Which sets are equivalent? Well, remember, the cardinal number of A was 4 and the cardinal number of D was 4. So A and B are equivalent. Okay, let's see. Cardinal number of B was 3. The cardinal number of C was 3. So they're the same size. So we can say that B and C are equivalent. B and C are equivalent. They're not equal. Remember, they weren't equal, but they are equivalent. They have the same number of elements, 3. On the other hand, A and D were equal. They had exactly the same elements. So if A and D have exactly the same number of elements, they've got to have the same number of elements, don't they? So here it's no coincidence that A and B were equivalent. In other words, they have the same number of elements. Well, of course they have the same number of elements. They have the same elements, period. Now we're going to finish up this discussion with some special sets. I guess this is well defined. New England states, what is that? Maine, Vermont, New Hampshire, Massachusetts, Rhode Island, Connecticut. Continental United States, those are all of the United States except Alaska and Hawaii. So 48 of the 50 states are in here. C, the southeastern states, what would that be? Maybe North South Carolina, Kentucky, Tennessee, Georgia, Florida, Alabama, Mississippi, and we might include Arkansas and Louisiana. Now these are 3 sets of states, and in each case we're talking about sets of states of the United States. So our universal set, whoops, I left something out here. Before I continue with this example, let me mention something up here. The universal set is denoted by a bold-faced capital U. That's how we denote the universal set. U for universal. Okay, back to our example. A is the set of New England states, B is the set of continental states, C is the set of southern states. In this example, every set seems to be a set that contains states of the United States. So, the set of the set of all objects or elements under consideration appears to be the set of all states of the United States. So our universal set is the set of all states in the United States. Now, do we need another example, maybe? Oh, no, I'm running out of inspiration here. What else is there? Well, let's see. These all seem to be sets whose elements are grocery stores or stores that have grocery stores in them. So our universe would be the set of all grocery stores. So the universe is the set of all objects under consideration. One more special set. The empty set, and this is how we denote the empty set, is the set that contains zero elements. It's the unique set, the one and only set that contains zero elements. Excuse me, I had to check something out. There is another way to denote the empty set, and that is open and closing brackets with nothing in between. So this is a set, but where are the elements in the set? They're not here because there are no elements in the empty set. So this is an alternate way of denoting the empty set. let's see. Before we work this out and see what this set really is, let's translate. A is the set of all elements X. How do we translate this vertical bar again? Such that, right? Such that this says X is an element of the real numbers, or we can just say X is a real number. And X squared is less than 0. So that's the literal translation. It's a little bit awkward. So I'm going to polish this up a little bit. A is the set of all elements X such that X is a real number. I can just say X is the set of all real numbers, or rather, A is the set of all real numbers X such that X squared is less than 0. Now think about this. What real number do you know of that you can square or multiply by itself and get a negative number? If we take a negative real number and multiply it by itself, we have a negative times a negative. That gives us a positive. If we have a positive real number and multiply it by itself, that's a positive times a positive, which is a positive. And if we have 0, which is neither negative nor positive, and we multiply it by itself, we get 0. So if we square a number or multiply it by itself, we either get a positive number or we get 0. If we take a real number and multiply it by itself, we never get a negative number. So the set of all real numbers such that X squared is less than 0, there are no such real numbers like that. There are no real numbers that we can square and get something less than 0. So guess what? This set A, the set of all real numbers X, such that X squared is less than 0. What's another way of writing it? A equals the empty set, the set with no elements. Well, that pretty much concludes our first lecture, everybody. But before we sign off, I'm going to give you some exercises from your text to work on, okay?